in a little bit of detail. So broadly speaking, the types of machine learning are supervised learning and unsupervised learning. Let us now take a look at each of these in more detail. So supervised learning is very much like learning under the watchful eye of a teacher who will point out to you when you're doing something right and when you're doing something wrong. A supervised learning algorithm also needs a lot of data along with responses. For example, a set of emails along with a verdict of whether those emails are spam or ham. You could in fact say that supervised learning is very much like viewing a number of questions along with the correct answers, and from that, learning to answer similar questions in the future. So supervised learning can be used to solve two kinds of problems, one of which is classification. This is when your response can fall into a number of discrete categories. For example, whether an email is spam or ham. In this particular case, since there are just two categories, we will say that it's a problem of binary classification. Of course, we may have more than just two categories. So, for example, whether an animal happens to be a mammal, fish, reptile, bird, or amphibian. The other kind of problem which supervised learning can solve is that of regression. This is where your responses are not limited to a number of discrete categories, but may involve predicting a continuous value such as a number. For example, if you're running an e-commerce site, you may want to predict the income of your shopper depending on their shopping habits and other data which is available to you. What a supervised learning algorithm does is to link a cause to a specific effect. In fact, you can say that a cause is represented by x, which is called an independent variable, and then the effect is represented by y, which is a dependent variable. The job of a supervised learning algorithm is to map the relationship between x and y. Now for some more terminology, the independent variables or attributes which a machine learning algorithm focuses on are called features, and there are typically more than just one feature, and the collection of these features is called a feature vector. These are what are typically inputs to a machine learning algorithm. The feature vectors are also referred to as X variables, and the other names they go by are independent variables or predictors. So if there are a number of causes which result in an effect, you could say that the causes are represented by X variables. On the other hand, the values which a supervised learning algorithm tries to predict are called labels. Now, labels can take two kinds of forms. They could be categorical. This is when the problem we're solving is that of classification, for example, spam or ham. Or the labels can be continuous. This is when we are solving a regression problem and we may predict, for example, a numeric value. So these labels are also called Y variables or dependent variables. I can imagine that everything just seems a little abstract right now. So let us take a look at a concrete example in order to clarify these terms. What we have here is a data set which will be used by our machine learning algorithm in order to build a model to classify emails as spam or ham. So each of these columns represent the attributes of our data set. Now, an individual attribute along with a value represents a feature. The variable which our machine learning algorithm will try to predict is known as the target variable. And our algorithm will also require a set of correct answers from which it can learn and build a model. And these answers over here are known as labels. And these are the values of the y variables. And finally, the inputs to our machine learning algorithm are known as the feature vector or the X variables. So a supervised learning algorithm will have a training stage in which it will go through all the X and Y variables in the data set, and it will learn of a relationship between the two, which it will map as Y is equal to f of X. So this is the machine learning model, which in the future will be used to make predictions of Y given an input X. At this point, we take a look at some more terminology, which represents some terms which we have come across already. The first one is linear regression, which is a type of problem where we need to predict a continuous value, such as a number. So previously, we just referred to this as regression. Then there is logistic regression, which so far we have referred to as classification, and involves predicting a value which may fall into a number of categories. I realize this can all be a little confusing, but these are commonly used terms in machine learning, and it's better that you know what each of them represent. In linear regression, how does one express the relationship between x and y? Well, if there is just one x variable and one y variable, then we can use this equation, which many of you will recognize as the equation of a straight line. Rephrasing this, we say that f of x is equal to wx plus b. So with linear regression, it is said upfront that the relationship between x and y, represented by f, is linear. Now, if you were to have two x variables rather than just the one, then our equation would be that of a two-dimensional plane instead of that of a straight line. For the sake of simplicity though, let us assume we only have one x and one y variable in our training data set, and that all the data points can be represented like this, where we have plotted all the x values against the y values. The job of a supervised learning algorithm which uses linear regression is to learn the relationship between x and y, and then come up with a line which maps the relationship and looks something like this. So this represents the machine learning model, and in the future, it will be used to make predictions of y given a value of x. Now, how does our machine learning algorithm decide that this is in fact the best regression line which can be built from our training data? For that, we can consider this point x, y in our training data and see how it relates to the regression line. So if we were only to feed the x value of this point to our regression line, then it would predict a y value which is represented by y hat. You will notice that this predicted value of y does not exactly correspond to the actual value. So we can calculate the difference between the predicted and actual value of y, and this is called the residual. Now, if there were a number of points in our training data, which are represented by x1, y1, x2, y2, and so on, we can get the residual for each of them by calculating the difference between the predicted and actual values of y. So in order to get the best regression line, our aim should be to minimize the error given our training data. An example method to do this is known as the least square method. Here, we just square all the residuals and sum them up, and the aim is to minimize this value of the sum of the squares of the residuals. Now, this is a straightforward optimization problem. We won't be covering the details of that in this course, but it is enough for you to know that there are standard techniques available to solve it. We now take a look at some of the caveats when trying to use linear regression, starting with the fact that linear regression can only be applied when the errors in our data are normally distributed. So if the distribution is not normal, it means that the relationship between x and y is not linear. Also, in our example so far, we've only covered the use of one independent or x variable. But linear regression can also be used when we have multiple x variables.